All right, so how the heck do we solve these problems? All right, so we've started re-recording. So the answer is that we're going to use basically an approach called backtracking with recursion. Okay, so recursive backtracking, which we've already done for depth first search. When we kind of did that already with depth first search. But what this essentially means is that we're going to do a very smart version of brute force, which means that we're going to basically try all possible combinations and then back up when we get ourselves into a dead end, until we work ourselves into a dead end. Yes?
Is that going to take like a really long time?
It could possibly. But actually, Sudoku, I think, is NP complete if you generalize it out, which means it's a really awful problem. But because the chess, well, it could take a long time, right? But because the chessboard is 8 squares by 8 squares, so there's only 64 possible squares, and there are, and in Sudoku it's 9 by 9. There's only so many possible combinations, right? There's a lot, but we've got, there's essentially we've limited, the search space is limited. So if it was bigger, it might be a real problem.
And what could the potential
could be how many possible? Well, if we're doing it like just trying every combination, right? So let's take a look at the chess problem, right? So forget the details on this, but let's see if I can't work it out. So you've got 64 possible squares, and you've got 8 possible queens to choose from. So I think that's like 64 choose 8? No, or is that? No, it would be 64 times 63 times 62 times 60. So it would be 64, 63, 62, 61, 60, 59, 58, 57. So it would be all those numbers that I just listed multiplied together. That's the number of combinations that you would have to check if you were just doing pure brute force, which is a big number. Okay. That being said, what we're going to do is we're going to use recursive backtracking, basically to say we're going to place one queen. We're going to basically go a step at a time, and as soon as we find that basically we are being led into a dead end, we're going to rule out all the combinations that lead us down that path. We're going to rule out that entire branch of combinations, right? So if we're solving this puzzle like left to right, like we put a queen here, then we put a queen here, then we put a queen here, it doesn't matter what the rest of the 5 other queens are going to be, where the rest of the 5 other queens are going to be put. They're all going to be wrong, right? Because we've already got a wrong answer, so we can rule out all those combinations if all those positions. So it's like basically we don't have to try every single thing that goes through a maze, every possible path that goes through a maze, including. Sorry, the prosper comparison is like with our maze program. Essentially, we're going to rule out all the paths that basically would have us walking through walls, essentially, right? That you can't go through a wall, so any path that has us going through a wall, even if we just started it at the if our third move has us going through a wall, we can rule out all the other possible options after that because we can't walk through a wall. Make sense? So we're going to basically shrink that search space, which is somewhere in the factorial range. So this is the general. So believe it or not, there is a generalized algorithm for solving these types of problems, which looks like this little intimidating thing, which says Boolean solve board position. If there's nothing left to solve, return true. Then for every possible choice, if that choice is valid, mark that board at position with choice, and then if solve board position plus 1 is equal to true, return true. Otherwise, clear any choices on the board and return false. Okay, that looks terrible. In fact, it is terrible. In fact, it's easier to show this in practice by actually showing how this algorithm works on a Sudoku puzzle. And I like this one because it's very visible. Very easy to see how this works. So I'm going to go ahead and reset the puzzle. Okay, so the way this works is that in Sudoku, typically you should use logic, right? So there's no ones in this column, and there's no ones in this row, there's no ones over here. So 1 is potentially a thing I could put there. But basically, you can use logic and rule things out, like saying, hey, so we eliminate all the possibilities. What could possibly go in this square? And I think basically that it will allow us to. It does this for us possibly. Let's see, auto, right? It tells us basically, oh, Well, if we look at this square over here, right, the only thing that can go into this square is 1 because we've got 5, 6, 7, 8 over here, 9, 7, 4 over here, and 2 and 3 over here. That rules out anything going into the square but a 1, right? And then we just work from there. And that's the kind of logic you use, right? And the computer's already doing that kind of logic for me. You know, and that's kind and then you just work your way up from there. But honestly, that's what you have to do without the computer. And so the other way for the computer to solve it is actually kind of fun, which is that we're just going to solve it like if we really don't have any patience to try to exercise our mind at all and do any logic stuff, which is that essentially I'm going to try something until it works. So I'm going to go left. My strategy is basically solve this board. So I'm going to solve the Sudoku board, and my position is going to be, well, position can be whatever you need it to be. So in this case, it's row and column here. So my row and column is the top left of this Sudoku board. Okay. So for every square, I'm going to solve my square. I'm going to choose something that works for my square, and then I'm going to recursively solve the rest of the puzzle. Does that make sense? So that's my strategy. I'm going to solve my square, and then I'm going to tell the rest of the puzzle to solve itself. And if they tell me that they were able to solve it, great. Then I know my answer was correct. And if they tell me that no, we weren't able to solve the puzzle, the people I told to solve the puzzle, or the function I called to solve the puzzle, it will I'll know that basically what I chose was incorrect, and led the rest of the function calls to a dead end. So let me demonstrate. 6 I can skip because that's already filled out. 5 I can skip because that's already filled out. So here is our first thing. So I don't have anything over here, so let me solve this one. Can I put a 1 here? No, I cannot. Can I put a 2 here? Sure. And now I'll simply call solve on the next row, on the next column. Can I put a 1 here? No. 2 here? No. 3 here? No. 4 here? Okay, move on to the next one. 1, 2, 3, 4, 5, 6, 7, 8. Okay. Oh, cool. Okay. Oh, that didn't work. All the possible combinations were taken already. Okay, so I'm at a dead end. So here's what I do. I return false. So this returns false, this returns false, this returns false to him, right? And he goes, okay, so I've tried all the numbers from 1 to 9, so obviously I can't put a 9 here, right? So what he says is that this square goes, oh, I tried a 9 here, and then I tried to solve the rest of the puzzle. I can't solve a 9. I can't put a 9 here. So there's no other numbers I can put here, so I have to backtrack. Then this one goes, okay, 8 didn't work. What about 9? 9 works. Let's continue on. 1, 2, 3, 4, 5, 6, 7, 8. Okay. And then, nope. So backtrack, backtrack, backtrack. 5, 6, 7, 8, 9. And then we just continue forward in that manner. So what did we pass? And your computer can actually do this quite quickly. Even though for me it's going to take quite a long amount of time to do. Right? So we basically go for every possible thing we could put down over here. Okay? We try it. And if it works, we continue. And if it doesn't work, well, we've got to back up. Okay? So let's look at that algorithm again. Solve the board for position. So if the position is such that there's nothing left to solve, basically if I get to this point over here, right? If I get out of bounds on the board, basically I get into row 10, which doesn't exist. I'll know that basically that the only way I could have gotten here is that if I filled up all the numbers, right? So at that point, I'll return true to basically let everybody know we reached the end of the puzzle. We're done. Otherwise, so if for each possible choice that I can fill the square with, right? If the choice is valid, in other words, can I actually put it there, right? I check, is each choice valid? If it's not valid, right? I simply go on to the next possible choice, right? So 2 wasn't valid, so I go on to 3. 3 isn't valid, so I go on to 4. So 4 is a valid choice. Okay? So 4 is a valid choice. So in that case, what I do is I mark the position. So 4 is a valid choice, so I put 4 down in that square. Okay, that makes sense. And then if solve plus board 1, if solve board position plus 1 equals true. return true. Okay, that's the weird part that people have trouble getting their heads wrapped around. But I swear to God, it eventually does make sense, which is just simply saying that, so let's just look at this call over here. The solve board position +1. All this is saying is call solve on the next position, and we're still working on the same board we were before, right? The board, that's just what we're storing our answers in, right? So it's obviously going to get passed from one function call to another. Okay. Here we're going to, but here we're going to go on to the next column. Here there's nothing to fill out, so we go to the next column. Nothing to fill out, so we go to the next column. And then the next column tries the exact same thing. And if it can't fill it up, sorry, if it can't, so here we're at that position +1. It tried every possible choice. It couldn't, none of them worked. So it clears out basically anything that it would have anything that was put down there. So we hit backspace to do that. And then return false, which basically would return false to this function call over here. And since we got a false back, that meant that basically that my recursive call, that failed to solve the puzzle, right? If I got a false back over here, that means it fails to solve the puzzle. This is essentially the else clause in your maze solver, right? In your maze solver where you had to pop. If you popped in your maze solver if you got to basically do a dead end in your maze solver, you had to pop. And this is essentially what we're doing there. We return false. So that doesn't work. So we have to try another possible choice. And then if we're out of choices, we remove all the choices we could have put down and return false ourselves. Make sense? So let's go ahead and see how that works on with the maze solver. So let me pump out the maze over here. So here with the maze solver, right? We had a position, right? Which was the top left. We started at the top left, right? And we basically had 4 possible choices in the directions we could go. Could we go north? No. Can we go west? No. Can we go south? Sure we can. Okay, then we do the same thing. Can we go north? Well, we've already been there, so no. Can we go west? No. Can we go south? Sure we can. So we would push this on top of the stack, right? Here, instead of pushing it onto the stack, though, we're just calling the recursive function. We're calling solve maze again. Can I go north? No. Can I go this way? Sure. And basically, it will keep going this way until it gets to this dead end. Sorry, get to this dead end first. And it'll go, oh, it's a dead end. Return false. And he goes, okay, can I go this way? Return false. Can I go this way? Return false. Return false. Return false. Return false. Go this way. And then it'll find the maze again. So it'll find the exit to the maze. Basically, you tell it which directions it. Basically, it had 4 choices as to where it could go, right? Once we iterated through all of them and determined that we couldn't go anywhere, we would backtrack. So this is the same algorithm, believe it or not, that we use for depth first search. So it's just done with the stack being used, with your computer's call frame stack being used instead of an actual physical stack that you've created. Does that make sense to everybody? Or have I lost people? You look a bit, yes.
So when it returns false, and it goes to keep trying to lose from the previous.
Yes, when we return false, it will jump back over to here, right? So it'll go if solve board position +1 is equal to true. That will be false. So this if state, so the return true here won't activate. So we know that wasn't a valid. Actually, wasn't that choice, while it was valid, won't actually solve the puzzle for us. So we continue on to the next possible choice. And then we do the same thing if that was a valid choice. We call to see if that will solve the rest of the puzzle. Yesterday's puzzle was able to get quite far before I had to backtrack. It was able to get down into this row before I had to backtrack. And it's not as hard as it looks, but it is a bit. It is a bit of a. It's one again. If you use this algorithm, it's not as terrible as a problem as it looks. And I give you the algorithm rather than where I had like the first 2 semesters I taught this, which is that they had to figure out the algorithm for themselves, and that was a bit of a mess. time because I ended up having to explain the algorithm in the lab anyway. So I figured, why not just give you the algorithm and try working on it? So this is so why am I torturing you in such a manner, you might ask? Well, this is one class of recursive problems that get used when we want to teach students. Sorry, this is one class of like recursive problems when we really want to teach students about recursion and see how it can be solved. It's also a class of problems that are very popular as programming interview questions, which segues nicely into the next segment.